weld V-groove welded joint. Groove welds are a fundamental welding techniques used to join melt pieces by depositing filler material into prepared groove. This method is particularly effective for ensuring deep weld penetration and structural integrity, making it essential for welding thick material in industries such as construction, shipbuilding, and manufacturing. Types and importance of groove welds. A common example of a groove weld is the V joint, where the edges of the metal pieces are beveled to form a V-shaped groove. Typically, this groove is set at the 60-degree angle to allow for proper filler deposition and full penetration. Groove welds are especially necessary when welding materials greater than 3/16 inches in thickness, as they help achieve the required joint strength. For plates and pipes ranging from 1/4 inches to 3/4 inch thick, a single V butt joint is often used. This joint configuration ensures strong fusion and structural durability. The primary purpose of grooving is to create enough space for the filler metal to penetrate deeply and form a strong defect-free bond. Key factors influence groove weld quality. Several critical factors influence the effectiveness and strength of a groove weld. 1. Bevel face. Definition: the sloped surface created on the edge of the base metal when it is prepared for welding. This is part for the groove in a joint that help achieve full penetration and fusion. Effects on welds. A well-prepared bevel face ensures adequate face space for the welding electrode and allows proper weld metal depositions. If the bevel face is too small or too steep, it can lead to incomplete fusion and penetration. Any improperly prepared bevel face can result in weak joints and excessive weld metal consumption. Number 2. Root face. Definition: the shape and thickness of the root face land at the joint before welding. It helps control the amount of root penetrations. Effect on welds. A properly designed root face prevents excessive penetration or burn-through. If the root face is too small or a feather edge is used, the weld joint may be weak due to insufficient root reinforcement. A thick root face may prevent full penetration, leading to lack of fusion or incomplete joint penetration. 3. Bevel angle. Definition: the angle between the bevel surface and a perpendicular line to the metal surface. Effects on welds. A properly bevel angle follows for easier access for the welding electrode, ensuring full penetration. If the bevel angle is too narrow, welders may struggle to properly fuse the root, causing lack of fusion defects. If the bevel angle is too large, it increases filler metal consumption and welding time, leading to insufficiency. 4. Included or groove angle. Definition: the total angle formed by the two beveled edges of the base metal in a butt joint. Effects on welds. A sufficient groove angle allows key deep penetration and electrode accessibility, reducing the risk of incomplete fusion or cracking. A groove angle that is too large leads to excessive filler metal use and longer welding time. A small groove angle can restrict access and prevent complete fusion. 5. Root opening. Definition: the gap between the metal pieces before welding, which allows for weld penetration and root fusion. Effect on welds. If the root opening is too large, excessive filler metal is required and there is a higher risk of burn-through. If the root opening is too small, penetration may be insufficient, leading to lack of fusion defects. A precise root opening ensures optimal weld strength and integrity. 6. Parent metal thickness. Definition: the thickness of the base metal being welded. Effects on welds. Determines the amount of heat required for proper fusion. Thicker metals require multiple passes to ensure proper penetration and weld integrity. The thin metals are prone to warping and burn through if not welded correctly. 7. Size of weld. Definition: the combination depth of bevel and the root penetration when specified in a joint. Effects on welds. The size of the weld directly impacts joint strength and durability. Undersized weld can lead to weak joint that may fail under stress. Oversized welds increase materials and labor cost and may cause excessive residual stresses. 8. Weld toe. Definition: the transition area between the weld face and the base metal. Effects on welds. Sharp or poorly blended weld toes create stress concentration points, increasing the risk of fatigue cracks. Smooth transition improve load distribution and reduce the likelihood of cracking. 9. Weld face. Definition: the exposed surface of completed weld bead. Effects on welds. A uniform and smooth weld face indicates good technique and strong weld quality. Irregularities on the weld face, such as excessive reinforcement or undercutting, can lead to stress concentration and failure. 10. Weld beads or weld passes. Definition: individual layers of weld metal deposited during weld. Effects on welds. Multiple weld beads help control heat input, reducing distortion and prevent defects. Improper bead placement can lead to lack of fusion or excessive reinforcement. 11. Weld layers. Definition: the arrangement of multiple weld passes in a joint. Effects on welds. Properly layered welds ensure even stress distribution and strong joint integrity. Poor layering can cause stress buildup and internal defects. 12. Heat affected zone. HAZ. Definition: the area of the base metal that has been affected by welding heat but has not melted. Effect on welds can lead to changes in mechanical properties such as hardness increase, which makes the metal brittle. Proper preheating and post-weld heat treatment can minimize HAZ cracking. 13. Depth of fusion. Definition: the distance weld metal has fused into the base metal. Effects on welds. Ensure proper bonding. Insufficient fusion results in weak joints. Shallow fusion can cause weld failures and stress or load. 14. Depth of penetration. Definition: the depth to which the weld metal extends into the base metal. Effects on welds. Proper penetration ensures strong joints. Insufficient penetration can lead to lack of fusion defects. 15. Face reinforcement. Definition: extra weld metal deposited above the base metal surface. Effects on welds. Provide additional strength but should be controlled to avoid excessive stress concentrations. 16. Root reinforcement. Definition: extra weld metal deposited at the root of a weld. Effects on welds. Add strength but excessive reinforcement can cause internal stresses. Backing weld. Definition: a weld applied to the root side to ensure complete penetration. Effects on welds. Enhances joint strength and prevent defects in critical welds. 18. Weld cap width. Definition: the width of the weld face. Effects on welds. Ensures proper load distribution. Excessive width leads to stress buildup. 19. Weld metal. Definition: the material deposited in a joint during welding. Effects on welds. Determines weld strength, corrosion resistance, and durability. 20. Weld boundary. Definition: the interface between the weld and base metal. Effects on welds. Ensure proper fusion. Poor bonding leads to weak welds. Fusion line. Definition: the boundary where the weld metal and base metal fuse. Effects on welds. Ensures metallurgical bonding. Poor fusion leads to defects. 22. Actual throat thickness. Definition: the shortest distance from the weld face to the root. Effects on welds: determines load carrying capacity, insufficient throat thickness, weakness that joint. 23. Fusion zone. Definition: the area where base and weld metal completely fuse. Effects on welds: proper fusion ensures strong joints, incomplete fusion leads to failure. 24th. Design throat thickness. Definition: the theoretical minimum throat thickness required for a weld. Effects on welds: ensures the weld meets design strength requirements. Common applications of groove welds. Groove welding is widely used in various industries where high strength joints are necessary, including construction, used in structural steel fabrication, bridges, and heavy equipment manufacturing. Shipbuilding, essential for joining thick plates in ship hulls, ensuring watertight and durable structures. Pipeline and oil industry, applied in welding thick pipes and pressure vessels to withstand extreme conditions. Manufacturing, used for fabricating machine components and large assemblies requiring strong durable connections. Conclusion: groove welds provide exceptional strength and durability when welding thick material. By careful considering factors such as root opening, groove angle, and penetration depth, welders can ensure high quality joints that meet industrial standards. Proper execution of groove welds prevents defects, enhances structural integrity, and ensures the longevity of welded components across various demanding applications. Thank you for watching. Please like, comment, share, and subscribe.